Okay, this should be my last video out here on the coffee table before all this stuff goes in the shop. In this one, we're going to cover LinuxCNC from the software side. So if you find yourself needing more detail than what I cover in this video, firstly, you are welcome to comment below and ask for follow-ups, and I will do my best to oblige. And secondly, there's a few other resources I want to point you towards. One of them is here on YouTube. There's a user by the name of RustStuff who's already done a 6-part video series on LinuxCNC. It was pretty high level, very well done, very approachable, and I actually found it pretty useful myself. So I do encourage you to check that out. Best of all is that this guy is also just another, Joe working in his garage, just trying to have some fun and demonstrate that DIY CNC is a totally doable thing. Secondly, there's the documentation for LinuxCNC, like the actual official documentation. I know it's crazy to recommend reading it, but trust me, for this project, it's good stuff. As a software engineer, I have seen far more popular projects with far worse documentation, so kudos on LinuxCNC for doing it right. The PDF version of their docs are like 750 pages, so it's very thorough, but it's also very well organized. So it's pretty easy to go through there and find the information you need, and large swaths of it are written in a way that it is approachable by non-software engineers. You will need some technical background, obviously. Like if you don't know, what a CPU is, you're going to be a little bit lost. But it's a much easier read than you would, think at first. So don't rule them out. Okay. And lastly, there are the LinuxCNC forums. For some reason, they have a lot of users there who are very bright and very experienced with the system, but who don't really branch out on other media platforms. As far as I know, there's really not much on YouTube about LinuxCNC and how to run it, apart from Russ's stuff and the stuff I'm working on now, which is why I'm trying to add my 2 cents. But if you do have other questions, the guys over there are a great resource, and I encourage you to sign up and ask away. Well, those are all great resources, and actually where I learned my information from. I still want to do my own overview of it, just because there's some things that I think deserve some special attention. Also, I have the benefit of running my demos on physical hardware. Let me explain. In Russ's videos, he was running LinuxCNC on a virtual machine with imaginary motors. So a virtual machine is a program you run on your host operating system that lets you run an entire guest operating system as a single program. So he was running the entirety of LinuxCNC in VirtualBox on his Windows machine. Now that works, kind of. You can run the software, but you can't control the motors, because the whole virtualization thing between Windows, VBox, and Linux messes with the real-time requirements of running CNC motors. So what I have here is a physical desktop machine with physical motors. It's just the whole gantry table part that's still imaginary. But we'll get there. Give me time, we'll get there. Now I'm also going to try to do something different this time, which is combining the video I'm recording with the audio I'm recording with what's actually on my screen. Now I can do that because on the desktop with LinuxCNC, I've also installed a VNC server that lets me log in remotely and stream it from my laptop. And then with another program called VNC to FLV, I can also take that streaming desktop image and save it straight to a video file. Cool, huh? So this is LinuxCNC. You have your desktop, your menu bar. Really, it should be a very, familiar computer experience. Now I'm going to gloss over the install steps pretty quickly because Russ already covered it pretty well himself. And this is essentially a variant of Ubuntu, which means any of the 50 billion Ubuntu guides out there online will pretty much have you covered. But the gist of it is, you go to linuxcnc.org, go to the downloads page, and get yourself the ISO. So this is basically a copy of the installation CD all dumped into a single file. You can either burn that to a CD, or you can put it onto a live USB stick. Once you have that ready, you restart your computer, and you hit the shortcut for like F12, F10, F1, whatever message it flashes to select your boot device as you start your computer up. Hit that shortcut, select your USB stick, and you'll be back here. And you'll have an instance of LinuxCNC running live off your USB stick. So the only difference from what you see Right here is there'll be a shortcut to actually install it on the hard drive somewhere over here in the desktop. Now that install process is important because while you're running live from the USB stick, any changes you make will not be saved. That's simply for test driving and actually installing the OS. So once you're ready to install it, you go through the menus and it's pretty self-explanatory. The only thing you gotta watch out for is that when you install it on the hard drive, it'll wipe everything else that's already there. Anyway, once it's installed, you reboot, remove the USB, and you'll be back here with an instance of LinuxCNC running straight off the hard drive. Obviously, LinuxCNC can't magically tell what our setup is, so we have to tell it. And that is where the Stepconf Wizard comes into play. So applications, CNC, and Stepconf. This will give you a fairly standard configuration file that will cover the majority of basic use cases for parallel port breakout boards and stepper motors. If you're doing anything fancy with like servos or Mesa hardware, then this program is not for you. And to be honest, this video is probably not for you either. We're only covering the basics, and that should cover the majority of people. So getting started, I already have a configuration file, so we're gonna run through that one. If you're doing one from scratch, then all the menus will be the same. You just have more information to fill in yourself. Now you're gonna want the shortcuts, which pop up here later to make it easier to actually launch the motor controller. And then for the hardware configuration, we are not going to make simulated hardware because I already have physical hardware out here on the table. Picking the file I've already done before. And now the name should be fairly obvious. And for the axes, we only need X, Y, and Z for a gantry table. And in fact, for this demo, I only have X and Y hooked up, so we're going to skip over Z when it comes to that. But anyway, let's see. And we're going to do inches because America. And then if you have one of these popular drives, you can pick that from here and it will fill in the timing information for you below. For everyone else, you have to go online and find these numbers yourself. Luckily, there is a wiki page that already has the timing info for a large number of boards, including the DQ542MAs that I picked. And that's double lucky. So you go to the original web page where they had that information before, you can see that it is no longer there. And it was probably in Chinese originally anyway, because yay, Chinese import companies, right? Anyway, before you buy your drives, you want to make sure you can find the step time, space, direction hold, and direction setup times. The question of, does LinuxCNC support my stepper driver, is the same as, can I find these numbers? Because LinuxCNC doesn't know what brand stepper is on the other end of that parallel port. And the driver doesn't know what's sending the signals either. Whether it's like LinuxCNC or Mach or Gerbil or like magical gnomes that have telegram switches sending Morse code, it doesn't know and it doesn't care. All it cares about is getting the pulses with the right timing. So just be sure you can find this timing information so that when you come to this part of the Stepconf, you have the right numbers to put in. It's also worth noting that this GUI assumes you use the same driver for every axis. Again, because this is covering the majority of basic use cases. If you do have different drivers, say because your X and Y are bigger axes and your Z is something smaller, then you can change that with manual configuration after it's already made the template config file. But we're not going to get into that in this video. The base thread jitter down here is for setting the amount of timing slop that LinuxCNC has to account for. You see, we're using the computer itself to make the signals for our drives. Now, when you're on the computer and you have multiple programs all running at the same time, it looks like they're running concurrently, but in reality they're not. The computer just switches back and forth between them really, really fast. But the switching isn't always consistent, and that's why sometimes you have a program that like brings your computer to a grinding halt until you finally manage to close it out. Because for some reason or another, that program decided to stop playing nicely with the other programs and began to hog the CPU. LinuxCNC is special in that it uses some very low-level modifications to the Linux code that provide a feature called RTIA, the real-time application interface. That makes the context switching more consistent and gives us a reliable series of ticks for issuing our signals to the drivers over the parallel port. Now, these low-level modifications are also why you're not going to use a regular Linux distro for running a CNC machine. So if you already have a computer with Fedora or Ubuntu or Mint or any other Linux distro, you probably aren't going to use that for your CNC machine because applying those kernel patches is such a royal pain in the ass. That is why the LinuxCNC guys came up with the ISO install, because that packages the entirety of LinuxCNC and the modified kernel all as one unit. Now, even with RTIA on LinuxCNC, we still have some slop. And to measure that, we run this program here. So this number down here is basically a measure of the worst case scenario time of how long we have to wait before telling LinuxCNC to output or to read a signal from the parallel port. And I personally know that if I let this run for long enough and do enough stuff in the background, then eventually I'll hit 15,000 nanoseconds, which I've then copied down to here. So these timings are based on the drives you have, and this one is based on the computer you have. Now, these values are just facts of life, really, and you can't update them arbitrarily. To actually change these values, you have to replace the hardware with better hardware that has better timing values. But luckily, even some very affordable, very basic equipment can get us good enough timings for a home gamer CNC setup. Now these times come together to form your min base period, and that determines how many steps per second you can do, and then eventually how fast your machine can go. So as an example, we can see here how 20,050 nanoseconds comes from 15,000 and the 5050 up here. Now if we go to a calculator, and we look at 20,050 nanoseconds, that's 10 to the negative 9, that is the duration for a high or a low pulse, for how long it must hold that signal to be sure the driver got it. So to look at a complete cycle of both a high and a low pulse, we multiply by 2. Now if we consider how many of those you can get in 1 second, and run the calculation, then that's 24,937. Now, lo and behold, 24,937. Now, that is the number of complete cycles you can get per second. Now, a stepper will step on both the high and the low part of the cycle, which means in reality, we're getting 50,000 steps a second on some very affordable hardware. Really, it is amazing what you can do with technology nowadays. For more detailed explanation of the min base period, I would say to look to Chapter 7 in the LinuxCNC documentation. That goes into all about steppers and how to optimize the performance. And then Chapter 8 following that actually has a lot of information on how to manually edit your configuration file to make it do what you want. It also has some cool tricks in there, like the latency plot, which I never would have heard of if I hadn't read the docs. So again, I do encourage you to take a look at that, because there might be some things you learn. Anyway, moving on. On this page, we set our pins. Now this will come pre-configured with a whole bunch of stuff. And if you haven't done the wiring yet, you're welcome to do the wiring to make it match the defaults. But if you have done your wiring, then change the defaults to make them match reality, right? Now if you watch the other video I did last, the one on the electronic side and how the wiring works, then my selections here will make a lot more sense. On pin 1, I did the relay from my plasma torch, and that is effectively my spindle. As I mentioned in that other video, the relay is kind of weird in that it takes a low signal to trigger rather than the usual high signal. So I also had to hit the invert button to make it work. Then we have the X and the Y, and then there's no Z and there's no A for now. Let's see, no spindle control for a plasma torch, obviously, and also no coolant. Now the E-stop out is interesting because you can use that to trigger an output signal when you hit your E-stop, either from the graphical interface in software or with a hardware button that you wire up to a parallel port input pin. Now this will let you do things like disabling your stepper drives when you hit the E-stop button, or if you're using a 3-phase motor on a lathe, you can send the E-stop out to your VFD and then program the VFD to turn off the motor when you hit your E-stop. So it gives you, some options to make your E-stop stop more things. Now on the input side, I have that input in, as I mentioned before, and that is also inverted to make it work when we are constantly syncing a signal to ground. There's more documentation on how to set that E-stop and your limit switches up in chapter let's see, it was 3.7.11.3 in the official LinuxCNC docs. Yes, 3.7.11.3. Like I said, it's very thorough and very organized. So look there for more information if you want to read about the e-stops and limits. Let's see. Now you can also add, limits and e-stops. Now I don't have any of those on this coffee table because nothing's actually moving to trigger a limit, but we will talk about more of these later. So moving on, here are some graphical settings we don't really need to care about right now, but they will let you do more advanced GUI setups later on if you want. And then we are here at the AXIS configuration. So now it's time for some math. My motors are 200 steps per revolution, and the drivers are set for 8 times microstepping. I'm going to hope that works because my lead screw pitch is pretty awful. In reality, I have a timing belt, and that has 3 millimeters in between teeth, and 24 teeth on the pulley that drives it. That means it's 72 millimeters per revolution. Now you divide that by the conversion to inches, and it's a little bit less than 3 inches per rev. Or in other words, about 1/3 of a rev per inch. Now you combine that with the microstepping, so times 1600 steps per revolution, and that gives us 564 steps per inch. Ta-da! Or about 2 thou per step. Now that is actually pretty friggin' coarse, but we are talking about a plasma in my basement, not a lathe making parts for the International Space Station. So I'm going to try it and see how it goes. If you remember back a few pages ago, we had 25 kilohertz for a full wave signal. That would be 50k steps per second. At 500 steps per inch, that would be a theoretical 100 inches per second, which is fucking insane. And your motor torque would almost certainly fall off well before those speeds. So it seems like the LinuxCNC guys have put some limits in here to keep you from testing your AXIS with anything too crazy. I haven't quite figured it out, but it appears as if anything above 10 inches per second does not let you run the test this AXIS tool. So for now, I'll set it back to 10, though I have tested before and found that 15 inches per second does actually work when I open up the AXIS program. In any case, even at 10 inches per second, that is still, 600 IPM, which is plenty enough for your rapids when your table is only 4 feet long. So now, once you have this set up, if your power supplies, drivers, motors, all that jazz are all plugged in, you should be able to hit test this AXIS and make it run. And it'll just jog back and forth in a little plus or minus a half an inch. Once it's gone for a while, you can hit run again, make it stop, and then increase that by a little bit, and then go again. Now the goal here is to test the full range of your machine by slowly increasing the range you're testing, and then by also playing with different velocity and acceleration values to see how fast you can go and how far you can go while still getting performance, consistently out of your machine. You don't want it to rack up, you don't want it to stall, any of that, to see what you can get out of it without anything acting wonky, basically. For illustration's sake, let's consider another scenario, and say instead of the timing belt, I had a ball screw that was 35 TPI. Pretty fine. Now this will change the steps per inch by 100-fold. So instead, it's 56,000 steps per inch. Now when we can do 50,000 steps per second, that should mean our velocity is limited to a little bit less than 1 inch per second. So if you open up this, we can see we are now limited to a little bit less than 1 inch per second. So in a scenario like that, you'd probably just do away with microstepping. So take this guy and change it back to 1. Now our step per inch dropped by a factor of 8. Our precision per step also drops by a factor of 8. So where we did have 0.2 of a thou per step, now it's more like 1/10 of a thou. But still plenty fine. And more importantly, since we take 8 times fewer steps per inch, we can do 8 times more inches per second. So what was 0.9 is now 7.1, 8 times faster. And that's kind of how the whole pitch and timing and all that work together to give you your theoretical maximum speed. As for what you should get in terms of motors, lead screws, rails, etc., to maximize the precision, torque, and speed of your tool, personally, I used empirical engineering. And that's where you look at what other people have done, and you do something like it. If it works, then great. And if not, you just adjust the recipe and you try again. It keeps you getting your head wrapped up in doing calculations ad nauseum. And you don't need an engineering degree to monkey see, monkey do. Right? Now give me 1 second, and I am going to change these values back to what they were before. So down here, we set the work envelope. And if you have home switches, we can tell LinuxCNC where they are. Usually for a gantry, you define everything in positive coordinates with homes at 0, and there they double as a limit switch. If you're doing a mill, you might have both positive and negative X and Y with a home in the middle. So that would mean you have a limit at either end and a home for 3 switches per axis instead of 2. And then your Z for a mill might be positive or only negative depending on how you like to do your CAD. Now the thing is, you can get by without these homes and limits at all. But then you have to manually home your machine every time you load the software, and that is not repeatable in the slightest. It might be convenient, but it just is not repeatable. So physical homes are a good idea. And then for the limits, the software will double check your motion to see if it goes past the table travel you list here. But it is still a good idea to have hardware limits just in case you fuck up. Now here we can set how we treat the homes, but I can't actually change these values now because I don't have any homes wired up on the pin configuration from a few pages ago. But the location is pretty obvious. The speed at which you search for a home is also pretty obvious. You want to move slowly so you can find it with precision, but not so slowly it takes forever. And then the style of latching has to do with whether you count the latch when you first touch a switch or when you back off the switch, or if you touch into it, then back off and touch into it again. Really, those shouldn't matter too much. Just run some tests and see what's repeatable. All right, so now I think we can move on to the y-axis, which is all the same, apart from changing the table travel, because my table will be roughly 3 by 4. And then the z is left undone because I don't have a z yet. And then there's no spindle to configure. So with that, we are done with configuration. Let's run this shit. So you double click the shortcut that the Stepconf Wizard left for us, and that begins EMC. This is the controller, and the AXIS GUI to the controller. There are other GUIs and other panels you can add to this, but that's stuff I haven't really gotten to yet. So for now, we're going to power on the machine in software, and then manually home it because I don't have home switches to use. So X, Y, and Z, and then we can use the arrow keys to move the motors around, or we can use these buttons here, turn the relay for the plasma off and on, or we can go to this stage and enter in G-codes manually. So if I type in something like G0, F500, X, let's say 48, Y36, that should move the arrow here from this corner to the far corner at 500 inches per minute after it accelerates. So, and we zoom out so you can see better. And sure enough, the little marker here on our software moved all the way across the workspace, and the motors turned just as well. So if you try another command, like G0, now to X50, Y40, which is beyond the work envelope, sending that should give us an error. And indeed, what? Oh, the wrong error. I typed it wrong. X50, Y40. This should give us an error. There we go. And it tells us that the move on each axis would exceed your limits. So that's how those software limits work. Now we're going to load a G-code file, which is really just a copy of this LinuxCNC logo here, modified to make it more friendly to this prototype setup. So, loading this. Let's open this up somewhere where it's a little bit easier to read. There we go. So, this is G-code, but don't be intimidated. You do not need to be a pro in G-code in order to use LinuxCNC. By and large, people make this stuff nowadays by doing CAD to design their part and then doing CAM to process and spit out the G-code. So it's helpful to know a little bit just to do debugging and testing and that kind of stuff, but you do not need to be a pro in it by any stretch of the imagination. So what this script used to do was roughly engrave the letters LinuxCNC. It would turn the spindle on, drop the tool down, move it out along the letters, LinuxCNC, and then bring the tool up and turn the spindle off. I did a few simple changes to make it more plasma realistic for the imaginary plasma hooked up here. Now, I don't know G-code, right? So what did I do? Well, I went to Wikipedia and I looked at the article for G-code, where they have a handy-dandy list of codes. And by looking at that and looking at this, I can kind of follow along and figure out how it worked. So I did a few simple changes, the first of which was changing it to work in inches rather than millimeters. So scrolling down here, we can see there's a G21 command for programming millimeters. And I took that out and made it G20 instead. I also adjusted the scale to make it fit better. I looked at anywhere where there's a motion in the Z direction and pulled that out because I don't yet have a Z. I took the spindle on at the beginning of the script and spindle off and replaced them both with spindle on and off around every letter. And I also added a few delays around those spindles on and off. And that kind of represents the delay time for both piercing the plate and then for breaking the arc when you're done with the cut. And then I adjust the feed speed on all these motions to make them 90 inches per minute, which is a more realistic speed for a plasma. Now I think that was all I had to do. Yeah, so a couple little tweaks makes this much more realistic. So ideally you do this all in CAM software, but again, this is just testing, having fun, trying to learn. So now we can come back here to the motor controller and hit play, and fingers crossed, it'll chooch. So it pulls itself all the way back to 0, 0. Relay goes on, it delays for a little bit, and begins the cut. Tracing around the L. At the end, goes off, it waits, and it rapids to the next letter. Look at that. And I think that's all for now.